Hello everyone. Today is the audio visualized recording for the physical chemistry of the topic the distribution law. The book writer is Dr. S.C. Khetrapal. The publication is Pardeep Publication. Introduction. Definition of the distribution law. It is observed that when a solid or a liquid is added to a mixture of two immiscible liquids, in both of which it is soluble, iodine to a mixture of carbon disulfide and water of succinic acid to a mixture of ether and water, it distributed itself between the two solids in such a manner that the ratio of a concentration of the substance in two liquid is always constant at a constant temperature. The observations were made by Barthelot and Jungfleisch in 1872. However, it is pointed by the Nernst in 1891 that the ratio of the concentration is constant only when the solute has the same molecular weight, that is, molecular state, both the solvents. Hence, the generalization was put in the proper form by Nernst, and it is called Nernst distribution law. It states as follows: a solute solution or a liquid distribute itself between the two miscible solvents in such a way that the ratio of the concentration of a solute in the two solvent is constant at constant temperature, independent of the presence any other molecular species, provided that the solute has the same molecular state in above the solution, that is, solute X distributed itself between the two immiscible solvents A and B, then its X remain in the same molecular state in both of the solvent. We will have the constant K is called distribution coefficient or partial coefficient. Concentration of X in solvent A upon concentration of X in solvent B is equals to C1 by C2 is equals to K, a constant. The test of a validity of the law. Different amount of a solution of iodine may be added to mixture of water and carbon tetrachloride taken in different bottles, thus are then shaken and allowed to stand. A known volume of each layer is pipetted out and then titrated against hyper solution to find out the concentration of iodine. Similarly, experiments may be performed with other solute and immiscible solvents. A few results of some earlier experiment are given in the next page. Condition under which distribution law is valid. The distribution law is valid only if the conditions are satisfied. The temperature must remain constant throughout the experiment. The two liquids solvents should be mutually immiscible. The amount of the solute added should be small. The solution should be dilute. This is essential because in certain cases the solute added affect the mutually solubility of the solvents. The solute must have the same molecular state in both the solvent. It should not undergo dissociation in any of the solvent or combination with any solvent. Thus the law is for the distribution of benzoic acid between water and benzene, because it has been observed that in benzoic undergo association to form dimers. It exists in C6H5COOH whole twice. Similarly, that is also not valid for distribution of electrolyte like HCl acid, because water and non-polar like benzene, CS2, CCl4, etc., because the electrolytes undergo dissociation in water. Thermodynamics derivative of the distribution law. The thermodynamics derivation of the distribution law is based upon the principle that if there are phase in equilibrium, two immiscible solvents containing the same solute dissolved in them, chemical potential of a substance present in should be same in both the phases. From thermodynamics, we should have the chemical potential mu of the substance is a solution given by mu is equals to mu naught plus RT log of A, whereas mu naught is the standard chemical potential and A is the activity of the substance solute in the solution. Thus, for the solute in liquid A, we have mu A is equals to mu naught A RT log of A. Similarly, for the solute in B, mu B is equals to mu naught B RT log of A. But A already stated, since the liquid A and B are in equilibrium, mu naught is equals to mu B. RT log of A is equal minus RT log of B is equals to mu naught B minus mu naught A. Further, a given temperature mu naught A and mu naught B are constant for given substance in the particular solvents. It constant temperature we have from equation 4. Log of A upon log of AB is equals to constant. This is the exact expression for the distribution law. However, if the solvent are diluted, the activities are equal to the concentration, so that the expression is modified. Ca upon Cb is equals to constant. That is original form of distribution law. Change in the molecular state in distribution law. As mentioned earlier, Nernst was the first person to point out the distribution law in the form of C1 by C2 is equals to constant is applicable only if the solute remain in the same molecular state. Both the solvent does not undergo association or dissociation in any of the solvent combination with any of the solvent. If, however, such changes take place in any of the solvent, then the law cannot be applied to the concentration of the solute in two phase, but only to the concentration of identical molecular particle in two phases. In each of the cases, the distribution law equation is modified as the discussed below simple cases. Case 1. When the solute undergo association in one of the solvents. Suppose the solute X remain in the normal molecular state in the phase, but N molecules of its associate to form complex molecule Xn in phase second. Then the following two equilibrium will consist simultaneously. Suppose that total concentration of the solute X is phase 1 is equals to C1. The total concentration of solute X in phase 2 is equals to C2. Also, suppose alpha is the degree of association of the solute in phase second, then concentration of associate molecule in phase second is equals to 1 by Nc2 alpha, and concentration of unassociated molecule in phase 2 is equals to 1 minus alpha C2. Applying the distribution law, we get concentration of solute X in phase 1 upon the concentration of normal molecule of X in case second is equals to constant. C1 upon 1 minus alpha into C2 is equals to constant. Again, applying the law of chemical equilibrium to equilibrium, we get concentration of associated molecules in phase second upon the concentration of normal molecule in phase second whole n is equals to constant. 1 minus Nc2 alpha upon 1 minus alpha C2 into n is equals to constant. Dividing both the equation first and second, then we get C1 upon n power C2 whole root C2 alpha. Alternatively, the same result may be obtained for a simple manner as follows. Suppose concentration of a solute X in first phase is equals to C1, concentration of associated molecule in phase second is equals to C2. Concentration of the simple molecule in phase second is equals to C3. Applying the distribution law equilibrium, we get C1 upon C3 is equals to constant. Again, applying the law of equilibrium to equilibrium, we get C2 upon C3 whole power n is equals to constant. Taking the nth root of the both side, we get n root C2 upon C3 is equals to constant. After that, we can divide it third and fourth equation and we get C1 upon root and C2 is equals to constant, which is the same as derived above. This is the such case when the solute undergo association one of the following solvent. The concentration of the partition coefficient is obtained not for the ratio C1 upon C2 but for the ratio of C1 upon n root C2. This relationship been confirmed by the studying of distribution of benzoic acid between water and benzoic, mainly associated molecules in benzoid solution. The following results are given below. Application of distribution law. The distribution law has been applied to the study of problems of the both theoretical and practical interest of the which we briefly discussed below. In calculating the solubility of a solute in a solvent, when two immiscible solvents are in contact with each other, solute is added in a such large state that the saturated solution are formed, then the concentration of the solution in the stage will be equal to their solubilities. Assuming that the distribution law is applicable for the condition, we will have C1 upon C2 is equals to S1 upon S2 is equals to K, where concentration C1 is equals to S1 is the solubility of the solute in solvent 1 and the concentration C2 is equals to S2 is the solubility of solute in solvent 2. Thus, knowing the distribution constant coefficient K and the solubility of the solute in one of the solvent, that can be other be calculated. In studying the extent of the association or dissociation of the solute in a solvent, we have already seen that there is a when a solute undergo association in one of the solvent, which is total concentration is C2, and has the normal molecular state in the second solvent is the concentration is C1. Then distribution law follows is modified as C1 upon n root C2 is equals to K, the distribution coefficient. From this formula, the value of n can be calculated by either hit and trial method by the logarithm method. First, the hit and trial method. The values of C1 and C2 obtained in the different experiments did and put in the C1 and n root C2 is equals to K. Then putting the n is equals to 2, 3 and 4 etc. one of the one. The values of k are calculated in each case. The number which gives constant values for k, the correct value is n. Logarithm method. The formula of finding n is equals to c1 upon root n k is equals to k, and c1 is equals to c2 1 upon root n. c1 is equals to c2 whole power 1 by n is equals to k. Taking log both sides, log c1 is equals to 1 by log c2 plus log k. For two sets of values c1 c2 and c1 dash c2 dash, we have log c1 is equals to 1 by n log c2 plus log k. 1 by log c1 is equals to 1 by n log c2 plus log k. Subtracting equation second f from the equation 1, we get log c1 minus log c1 dash is equals to 1 by n log c2 minus log c2 dash. N is equals to log c2 minus log c2 dash upon log c1 minus log c1 dash. Hence n can be calculated. Similarly, when a solute undergoes dissociation in one of the solvents, X change into Y plus Z, in which its concentration is C2 at the same normal molecular state in second solvent, in which its concentration is equals to C1, then we have C1 is equals to C2 minus 1 minus alpha is equals to K, the distribution coefficient. From this formula, the degree of dissociation alpha can be easily calculated. The prediction distribution indicator. It has been seen that the iodine distributes itself between CS2 and the water distribution coefficient. Thus, if a weak solution of iodine is to be esteemed, then a few drops of CS2 may be added to this solution. As a result, a considerable amount of I2 will pass in C2S2 layer and give it the deep violet color. Now the solution may be titrated against hyposolution till the violet color in CS2 layer disappears. Thus iodine acts as the distribution indicator in this case. In the study of chemical equilibrium leading to the formation of complex ion, distribution helps us to determine the equilibrium constant for if any above equilibrium, and hence the establishment of the formula of complex ion on the basis of consistency in the value of the equilibrium constant. As an example, let us consider the first equilibrium reaction. The study of the equilibrium involves the following step. A solution of iodine in CS2 is shaken with the water to find out the distribution coefficient of iodine between water and CS2. A solution of iodine in CS2 of a known concentration is shaken in Ki solution also of the known concentration. After the distribution of iodine is complete between the two layers, the concentration of iodine left in the CS2 layer is determined by the result then calculated as suppose that after the distribution of iodine is completed between the two layers, the concentration of iodine less CSD is determined by the titrated against standard type hyposolution. The result is calculated as follows. Suppose that initial concentration of iodine is CS2 a moles per liter. Initial concentration of Ki is equals to B moles per liter. Concentration of I2 left in the CS2 layer of distribution is equals to C moles per liter. Distribution coefficient of the I2 between water is equals to CS2 is equals to K. As iodine react with Ki, the total observation of iodine free plus combined in the aqueous layer much higher than than if no Ki were present. Obviously, the total concentration of I2 in the aqueous layer is equals to initial concentration of I2 in CS2 minus concentration of I2 left in CS2 layer A minus C molecules per liter. Concentration free I2 in aqueous layer can be calculated by applying distribution law. Concentration of free I2 in aqueous layer, concentration of I2 in CS2 layer K distribution coefficient, but concentration of I2 in CS2 layer is equals to C moles per liter. Concentration of free I2 in aqueous layer is equals to Kc moles per liter. Amount of I2 that has been combined with Kia minus C minus Kc moles per liter d moles per liter. Now, according to the reaction, Ki plus I2 is equals to Ki3, number of moles I2 combined, and number of moles is equals to Ki compound, number of moles is equals to Ki3 formed. Concentration in the aqueous layer is equals to d moles per liter. Concentration of Ki in the aqueous layer is equals to B minus d moles per liter. Concentration of I2 in the aqueous layer is equals to Kc moles per liter. Substituting these values in equilibrium law expression with K dash is equals to Ki3 upon Ki I2. The equilibrium constant K dash can be calculated starting with the different initial concentration of iodine and Ki solution. The value of K dash is determined in the each case. If very constant is the value of K dash, confirm the formula of the complex Ki3 is equal or that of the complex ion I negative 3. In the process of extraction, the process of extraction of great importance both the laboratory and industry. In the laboratory, the process is often used for the removal of dissolved substance from an aqueous solution with the help of organic solvent like ether, chloroform and carbon tetrachloride of benzene. In the industry, the process is used to remove the impurity from the product. Basically, the process involves shaking of the aqueous solution of the substance with an organic solvent which is immiscible with water, but in which the substance extracted in the solution after shaking the miscible is allowed to stand. Most of the substance passes in the organic layer from which the farmer can be separated out, distilled of the organic solvent. However, in order that the process of extraction may be more effective and efficient, the following two conditions must be fulfilled. The value of the distribution coefficient of the substance between water and the extracting solvent should be greater in the favor of extracting solvent. It is sometimes possible to increase the distribution coefficient artificially by making the substance less soluble in the compound being extracted. Thus, suppose that the organic acid which ionizes to a certain extent in aqueous solution is to be extracted with ether. If a strong inorganic acid is added to the solution, the hydrogen ion concentrated is increased with the ionization of organic acid is reduced. Because of the common ion effect in the solution, there will be greater amount of undissociated acid and hence the amount extracted will be greater. Similarly, an organic base can be best extracted in the presence of strong inorganic base. The addition of salt also usually lower the solubility of an organic compound in water and thus increase the distribution coefficient. The whole of the extracting solvent available should not be used in the lot of but itself is used in a maximum number of installments. This is factor increase the efficient of extraction can be follows. Suppose x gram of substance are present in 1 liter of aqueous solution. Also suppose 1 liter of ether available as the extracting solvent, and then the distribution coefficient of the substance between ether and the water is 2. Now, if whole of the ether is used in one lot of X be the amount of substance extracted in the ether, then we will have concentrated in ether upon concentrated in H2O X upon 1000 upon X minus X upon 1000 is equals to 2. X is equals to 2 upon 3. X is equals to 0.67x. Thus, only 67% of the total amount will be extracted in the case. Again, suppose the volume of the ether is 2 installment. Each of is 500 cc. After shaking with the installment of 500 cc, suppose x1 gram of the substance pass through in the ether layer, then clearly thus 50% of the total amount is extracted from the operation. Therefore, the amount of substance left unextracted. Now, one of the little of the aqueous soluting containing of the substance is shaken, remaining 500 cc of ether. Suppose that the amount extracted in the ether is x2 gram, then 25% of the total substance in ether layer is the operation. Therefore, total amount of substance extracted 50 plus 25 is equal to 75%. Then when the 1 liter of the ether is used in equal installments, the percentage extraction increase from the 67.7 to 75%. Similarly, it can be 1 liter of the ether used in 4 equal installment. The extraction increase further to 93.75%. A general formula can be derived which gives the amount of the substance left unextracted after a definite number of operations. Supposed W gram of the substance is present in V ml of the solution made in solvent A. Also suppose that V ml of the extracting solvent B is used in each time, and K is the distribution coefficient of the substance between the solvent A and B. Now, if W 1 gram B with the amount of substance left unextracted in solvent A after the first operation, then again after the second operation W2 be the amount of substance left over and extracted is solvent, so the amount extracted is W1 minus W2G. Then putting the value of W1 from the equation. In general, after nth operation, the amount of the substance left and extracted will be Wn is equals to Kv upon V plus Kv whole n into W. In the order of extraction may be the most efficient. Clearly, Wn should be the smallest possible. This can be so only the factor is small possible. Now it is the factor that the denominator V plus Kv is the greater than possible when n is the largest number. So it follows that the multiple step extraction is more economical law in a single step extraction. Further, from the above equation it may be seen that Wn can never be equals to 0. However, large n may be. In other words, extraction can never be complete. However, large number of extraction may be carried out. Otherwise also it is clear that every time that the substance left distributes itself between the two and same quantity, however small, and must be left unextracted. Note: for the purpose of numerical problem, it must be remembered that the K distribution coefficient of the substance between the solvent A already present in the extraction solvent B. If K is given for the distribution of the substance between solvent B and A, the reciprocal of its value should be the used of the above equation. The principle of multi-step extracting holds good for the washing its precipitates, where the impurities distribute between the liquid and the precipitate. Further, it sparks process for the desilveration of lead, also used in made of principle of extraction, however is more soluble in zinc than in lead. Zinc is immiscible with molten lead, thus zinc is added to the lead. A large quantity of silver goes into molten zinc layer, leaving little silver of the molten layer. Because the distribution coefficient of the silver between zinc and lead is 300 at 880 degrees Celsius, zinc contains silver forms the upper layer. Thus, by repeating the process, almost total quantity of silver can be extracted from the argentiferous lead. In the determination of degree of hydrolysis, let us first study that some terms and expressions related to the salt hydrolysis constant. The general equation for the hydrolysis of a salt Ba may be written as Ba plus H2O is equals to Ha plus BOH. Applying the law of chemical equilibrium, Ha, concentration of Ha and concentration of BOH upon Ba plus upon H2O is equals to K is equals to equilibrium constant. Since water is present in very large excess in the aqueous solution, its concentration H2O may be regarded as constant, so that we have Ha upon Ha concentration of BOH upon Ba is equals to KH2 is equals to KH, where KH is the hydrolysis constant. Since Ha and BOH represent the molar concentration of the free acid and the free base produced, concentration of Ba represent the molar concentration of unhydrolyzed salt. The above expression for the hydrolyzed constant may be written in the more general way as Kh is equals to free acid free base upon unhydrolyzed salt. Degree of hydrolysis. The degree of hydrolysis of a salt is defined as the fraction or the percentage of the total salt which is hydrolyzed. For example, if in a solution of aniline hydrochloride 90% of salt is hydrolyzed into aniline and hydrochloric acid, the degree of hydrolysis is 0.90 or may be expressed as percentage with 90%. It is usually represented by the symbol H. H is equals to number of moles of the salt hydrolyzed upon total number of moles of salt taken. Expression of for the degree of hydrolysis for the solution of a different type of salt. As salt of strong acid and bases are not undergo hydrolysis, therefore to talk KH or H of such salt in meaningless. The cases of the other three types of salt as given below. First, salt of weak acid and strong base. Representing salt by Ba as usual, the hydrolysis may be represented as follows. Ba plus H2O gives BOH plus HA. B positive plus A negative plus H2O is equals to give B positive plus OH negative plus HA. It is a case of anion hydrolysis. Suppose the original concentration of the salt in the solution in C moles per liter in the H hydrolysis as concentration. Then we have original concentration at equilibrium C. The hydrolysis constant KH will therefore be given by, if H is very small to 1, if we can 1 minus H approx 1, so that the above expression is H congruent upon KH upon C. Thus the degree of hydrolysis of a weak salt H is inversely proportional to the root of 1 by C. Thus the degree of hydrolysis of a salt of weak acid and the strong base is inversely proportional to the square root of its molecular concentration. Salt of strong acid or strong base. For the salt Ba of the hydrolysis proceeding as in the earlier case, we can get some relationship. H is equals to approx k root KH upon C. Salt of weak acid and weak base. Representing the salt by as we have it involves both anion hydrolysis as we cation hydrolysis. Here the both relationship KH and H does not involve, thus the degree of hydrolysis such as is independent on the concentration of the solution. If H is very small in comparison to 1, we can take 1 minus H approx to 1, so the equation become KH is equals to H square, H approx to root KH. Determination of degree of hydrolysis by the application of distribution law. Suppose it is required to determine the degree of hydrolysis of aniline hydrochloride, which is a salt of weak base and a strong acid. The method consists of two steps as follows. First, determination of hydrolysis constant. Aniline hydrochloride is hydrolyzed as, the hydrolysis constant will be therefore given by KH is equals to free aniline concentration of free aniline, concentration of free HCl acid upon concentration of unhydrolyzed salt. Thus to get the value of KH, the aim to find the molar concentration of free aniline, free HCl as acid, and the unhydrolyzed salt in the aqueous solution of aniline hydrochloride of unknown concentration with benzene as a result. The free aniline distributes itself between the two solvent water and the benzene, whereas HCl and the unhydrolyzed salt remain in the aqueous layer as shown. A part. Calculation of concentration of free aniline in the aqueous layer. Thus for this purpose the concentration of aniline present in the benzene layer is found by taking a known volume of this layer, evaporating the benzene and finding the weight of aniline left. Having known the concentration of aniline in the benzene layer, that is the known aqueous layer, can be calculated. The distribution coefficient of aniline between water and benzene is known as, can be found by the separate experiment. Calculation of concentration of free HCl produced from the hydrolysis experiment equation. Number of molecules of HCl produced, total number of moles is equals to aniline produced, but total number of aniline produced is equals to amount of aniline present in the benzene layer plus amount of aniline present in the aqueous layer. Each of these amount has already been calculated in step A above. Hence the total number of moles of aniline produced by the free HCl produced can be calculated. Knowing the volume of aqueous layer, the concentration of free HCl in aqueous layer can be calculated. Calculation of concentration of unhydrolyzed salt. From the hydrolyzed equation, it is that the number of moles of the salt hydrolyzed is equals to total number of moles of the aniline produced of HCl produced, whereas already been calculated in step B above. Hence knowing the initial number of moles of the salt taken, the Number of moles of the salt left unhydrolyzed can be calculated. Further, knowing the volume of the aqueous layer, the concentration of unhydrolyzed salt can be calculated. Second, calculation of the degree of hydrolysis. Knowing the hydrolysis constant K is the degree of hydrolysis of a solution of aniline hydrochloride having concentration C molecule can be calculated directly from the expression H is equals to root KH upon C. Thank you.